open on the computer. Okay, perfect. Yeah, I am screen sharing as well. Okay, perfect. So yeah, cycles is, I'll just repeat for the recording. When you add an edge, that will always, in a spanning tree, that will always form a cycle. And the red rule is just looking at that cycle, taking the edge of max weight, and then basically saying like, this is colored red, this won't be in our MST. So the cut sets are something similar. If you group the nodes into like two batches, there's always going to be, there might be several edges between them. This is the cut set. So here it's this edge 8 and this edge 9. Now, because of the fact that the spanning tree has to connect all nodes together, there must be one edge between these two groups of nodes to create the spanning tree. And so what the blue rule just does is say, okay, you have this cut set with no blue edges. Essentially, you have the cut set where it hasn't been applied before. You just take the edge of minimum cost and color it blue. So here you'd say like, oh, 8, I want to color it blue. And when you're making the MST, you want those blue edges to be included. So cycles is just saying, here's a set of edges. I'll say, take the largest one. I'll say this can't be in my tree. And here's blue rule is just saying, here's a set of edges. It's a cut set. I want the smallest one to be in my tree guaranteed. What's up? Okay. Well, I'm assuming you're referring to like red rule, blue rule, right? So you don't, when you color an edge blue, like you don't color the other one red. I mean, here, like it's red, that's like separate from the actual rules. The coloring here is separate from the actual rules. When you apply the red rule and the blue rule, you only like color one edge. Is this what you're asking? So blue rule, when you select like the minimum edge between two cut sets. So again, you can say like this is your cut set. You would just color this edge blue, right? That's all you would do. And then similarly, if you're taking the red rule for like, I don't know, this cycle, like you would color this edge red, and that's all you would do. So yeah, did that answer your question? So yeah, you can kind of like know what this idea of the idea of like the cycle and how that relates to the red rule, and know the cut set and how that relates to the blue rule. Like they're pretty much the same thing. It's just like, oh, if I add an edge or take away an edge, like how will that make a difference? And I don't know if I actually did mention this, but like a cut set will always form if you take away an edge. So like if you take away this 9, that's when you'll kind of have that segmentation into two groups in which you're forced to take like one of these two edges, one of the two of the cut set. Okay, and so now we hopefully understand the red rule and blue rule a bit more. How do we actually apply this? So there's another thing to know called color invariance. And I don't know how much we actually have to know this because it was pretty confusing, I think, when he explained it in class. But basically, it's just a proof by induction to like discuss that or to prove that there's the MST will always like contain every blue edge and no red edge. And because it's induction, basically what he says is like, if we can start with it true and we can prove that after we apply the red rule, it's still true. And after we apply the blue rule, it's still true. We can like prove it's true overall. And basically the way he did this in class was he was saying, okay, let's go through, check the chat real quick. Where will this be posted? I don't know. I'll put it in the Discord. I'll put it in the Slack, just like in the same places where I like announce it. Yeah, okay. So if you apply the blue rule, right? Again, you want a cut set. So say you are like selecting like this as your cut set, which means that you now have edges F and E under the consideration. So if E is less weight than F, you're coloring the edge E blue. E is already in this like tree, so you're fine. If F is the one being colored blue, that means you would need to add it to your tree, but E is in the tree and forms a cycle because you can only have like one edge per cut set in your tree. So that means you'd have to remove E from the tree. Now, how do we do this while still like satisfying this? You can actually recognize that E has to be an uncolored edge. And that's because, one, you're applying the blue rule on this cut set, which means that inherently E cannot be blue because the blue rule literally says no blue edges in the cut set. So E can't be blue. And also E was in the tree, so it can't be red. So we know E is uncolored and we can kind of just swap it for F. Then this proof for red is kind of the opposite. So if you color this edge E red and it's already in the tree, we want to get rid of it. And so what we can realize is that like by getting rid of this, we can instead take the edge F, and we can do that because it's also uncolored, because of the fact that if you take it, it would form like a cycle, and like E is being colored red, so there is no, red rule says that like in a cycle, that cycle must have no red edges. So if you are applying the red rule to this cycle and coloring E red, there's no way that F could also be red. And it also can't be blue because it's just not in the tree. So I don't know if you'll actually have to know this, but it might still be a nice exercise to walk through with kind of like just recognizing the consequences of these two rules. Okay, and so what do we actually like learn from this? Well, through applying these rules, we can actually form a minimum spanning tree. Now, the simplest way to just do this is just Prim's algorithm, which is just applying the blue rule over and over and over. Because at the end of the day, the blue edges are what form an MST. Because you can think about it. Your blue rule always just selects the shortest edge in a cut set, so you want to accrue those blue edges. And so there was another proof here, which basically like said like, oh, the greedy algorithm will always terminate, and as long as an uncolored edge exists, it will like apply a rule. So the way he did this is by like looking at specific cases for edges. So if an edge has both of its endpoints in the same like blue group, that means it would form a cycle, and therefore the red rule could be applied. So in that case, we would just like color this edge red and be done with it. If edge had its ends in different groups, then that would actually be a cut set because we have one blue group and the other blue group, and we want to connect them. And so we'd end up using the blue rule. And so we wouldn't necessarily have to color like this edge blue. We could also color like this one blue or this one blue. That's not blue, but you get my point. And then there's some like little details too, like if an edge has like no blue ends, you can just like apply the blue rule, and like because of the way that like the rules work, like all the blue edges will end up connecting because there's like for every cut set there will exist like a certain blue edge. So basically, it'll work. And that leads us to the two algorithms that we actually discussed. One is Prim's, which is basically just saying you start with a node and you keep adding edges that come out of like the set of nodes, and you add the edges with lowest cost. So say you start with like this node A, you would say like, okay, what do I have under consideration? I have 3 and 5. 3 is lower cost, so I'll take that. Then I have 5, 4, 5, 6 in consideration. I'll take the 4. Then you can add these two into consideration. 2 is the lowest, so on and so forth. You do this 5 here, you did this 3 here. Yeah. Yeah, you would. Yeah, I was just like skipping ahead, but this is what the outcome would be. But yeah, it's always lowest first. And you can see that like what's just happening here is this is just the blue rule over and over, because you start with like a cut set that is just your source node, and then you say, okay, what's the lowest edge on this cut set? Yeah. Yeah, I was just saying, yeah, and then you color this blue, and then like this is your new cut set, and you're saying, oh, what's the shortest edge? And then you color this one blue, so on and so forth. Because this is like kind of just a general proof, and for prims, you will always have like one set to iterate out of, like Kruskal's, for instance. We'll get into it like just now. You may have several groups. So it may help if I just like do this. So here, Kruskal's, wrong one. What it does is it keeps adding the edge of lowest cost as long as it does not form a cycle. So I'll just say like, okay, here you'd start with 2. Let's say like this was like a 3 or whatever. And you could take this. And obviously you would want those in your minimum spanning tree. Those would be blue edges because they're of lowest cost. So you would have like these kind of two groups of blue edges. So that's kind of what would happen here. Yeah, yeah. So all of the blue, like all the trees of the trees, the blue trees would have to end up connected. Yeah, yes, yeah. Mhm. Yeah, it's basically saying like when there's an uncolored edge anywhere in the graph, like what can I do? And it's proving like you can either apply the red rule or the blue rule at any point. Um, and yeah, and that kind of like shows like why the blues will always end up connected because otherwise like all of the edges between the sets would have to be like red, and that's just like not possible because then that would like form a cycle with several red edges and whatnot. But yeah, I guess we can talk about crustals now. It just adds the edge with lowest weight if you're able to. So like this 2, you can just do. This 3, you can just do. Uh, where's 4 is over here? Oh, there's another 3 over here. Yeah, there's 3, and then there's 4. And then it kind of starts to get interesting. If both of the edges are in the same blue tree, so like take this 5, for instance, uh, we want to take it because it's a low weight edge, but because it's in the same tree, taking this would form that fundamental cycle. So what's effectively happening there is you're looking at the cycle and you're saying, I'm running the red rule on this. And because you're running the red rule, that edge that you're taking last is actually the one with like greatest weight. So you would end up like coloring that one red. I know my colors are completely mixed up here, but that wasn't my choice. So yeah, that would like end up being colored red. So essentially, like I can keep running through the like how this algorithm would run. Like this would execute, and at this point you've connected all your nodes. But then like this 5, it connects. It will form this fundamental cycle, which means that you're going to be end up coloring this one red instead of blue. Okay, divide and conquer. So I think this one, although being like conceptually much simpler than like DP or whatever, this is, I think, a fairly tough unit, especially with like the median of medians and all that. There's some rough stuff in here for sure. But let's see, does anyone online have any questions before I move on? Okay, cool. I'm hoping we don't get kicked out of this room because apparently the building now closes at 8. But, you know, we'll ball until then. Okay, let's continue. So for some reason, also, by the way, he did say 2 MST problems, 2 divide and conquer problems, 2 DP problems, and 1 network flow multiple choice problem. So you do have to kind of make sure you know everything, even if it's on an FRQ. And also being said, he did like put a lot of emphasis on merge sort for some reason, even though I think it's a pretty straightforward algorithm. So, you know, I hope you all kind of know what this does. So it will continually split the like array into halves. And then in the event where there's like one option that's inherently sorted. Hello, Jonas. No, this is an algo review. We're reviewing for algo. Do you have something like in this room? No, sorry. It's all good. Okay. What was I saying? Yeah. So when they're units of length 1, they're inherently sorted. So then you just like combine them back up. So like in this case, this 14 to 7, you would split into like 14 and 7, and then you would like take this. Oh wow, now it's combined. And this like 312 go like here. And then you can like merge them together, like, oh, this 3 and then the 7 and this 12 and this 14. It's fairly straightforward. And then the time complexity of this is always going to be n log n, I believe, because you're always going to be splitting in half and half and half and half. That will always be like log iterations, because if you split something in half repeatedly, that's just like number of logarithms. It's like logarithmic. And then the actual like interleaving the numerical arrays together is always n time. Okay. Person said 2 FRQs. Yes, yes. Network flow and knapsack. So yeah, this is pretty straightforward, and it's always going to be, I believe, n log n, right? Because you're always going to be breaking down the entire list and then combining the entire list. It doesn't really like check anything before it breaks everything down, and then it only will like check it as it combines stuff together. So it doesn't matter if it's like already sorted or all the same value, because no matter what, it's going to be breaking them into little pieces and then like combining the little pieces together. And that will always be like n time with like log n splits. Can someone put in chat what the 7 multiple choice topics are? Everyone. 2, MST. 2, divide. Can you hear me? Hi. What's up, Tony? 2, DP. 1, flow. There's your stuff. Okay. And then linked list shuffling. There's no something, I don't know if this is on the exam, but he like touched on this briefly in class. Basically, if you have 2 lists and you want to like sort their values randomly together, you just use a probability equal to like the number of values proportional in the list. So like here, say this is like n elements and this is like 2n elements. You'll have like the first element in your like randomized array will have like a 2n/3 chance to be like from here, and like a 1n/3 chance of being in here, just because there's like 2n more values in here. You can kind of just think about it like you want to have both of the arrays like end together. So you want like to take every 2 values out of here for every like 1 in here. And obviously this would have to be like adjusted on the fly. So say you randomly end up taking half of these values off, and now it's just as equal as this. They both have n left. Then it would be 1/2 for each. Yeah. Well, you don't, no, you don't, sorry, I might have explained that like misleadingly. It's not, you don't guaranteed like take it from the first list because you want it to be random. What you instead do is you say like, if I have like a list of like a bunch of elements and a list of like very few elements, if you did like half and half probability, like, oh, I have half a chance of taking it from the top and half from the bottom, what you would see is that the elements from the bottom would get like shoved into the start of the array, right? Because you might take like 2 from here, but then you would take like 1 from here, and then you would take like 2 from here, and then like maybe even 3, and then like 1 from here, and you would take all of these. So the ones from the small array would be like stuck at the start. So what you actually have to do is the chance you throw it into the results array is proportional to the size of the array, or like inversely, no, proportional. So like this is like a 2 times chance of taking an element from here and like a 1 times from here. Yeah. At the end of the day, you want it to be random. So you still want a chance for these elements to like come into the start of the array. You just want it to be less probable than those of like the larger array. Because think about it like this, like for every 1 element in here, you want like 2 elements from here to kind of like pad the gaps. And that's how you can kind of have that like equal distribution. What's up, Brian? Yes, that's a good question. They do change. And that's kind of what I was talking about with like the example where like say randomly, not because this is like how the algorithm works, you end up taking like all the top half or like the first half of the large array, right? And you end up with like n elements in each array. So you have like in your final array, you have like those elements here. You still want these two to kind of be like randomly interspersed. So now the probability does have to be equal between the two. So it's based on how much is left between the two. So bottom line, I don't think that will be in the exam, but just like try and think of it intuitively. Okay, if you have a large array and a small array, and you want the small array's elements to be like evenly distributed, the small array has to has an element of the small array has to have a lower chance of being put into the final array than the element of the larger array. Hopefully that will like makes intuitive sense to everyone. Because at the end of the day, like all that stuff he does like vary and make like variations for and whatnot. So it's good to just understand the intuition behind the algorithms. Man, I need some water. So the next thing, inversion counting, he presented it a little weird in the class, but like there's a way you're supposed to do it. By the way, this is a 3. It's a little, it's covered by the mouse, but yeah, this is a 3. So basically what you do is this is a divide and conquer algorithm with a linear time. This is kind of misleading. This is very misleading, actually. Forget I said that. Way of like combining them together. Yeah, of the total thing. And plus you have to sort these, so it's going to be n log n. The actual like combining is linear. Yeah. So the idea here is given a list of numbers, cheers, bro. That's goated. You want to know how many are essentially like out of place. So if 20 comes before 7, that's like an inversion because 7 is less than 20. And so at first you might say like, okay, if I add another like element here, like 6, okay, then 6 is inverted with this and inverted with this, and it's just a big hassle. You can like break it down, divide and conquer into smaller parts here. My 3 is going to get erased, rip. And so basically what you end up doing is just counting the number of inversions in here, say there's n, and then counting the number of inversions in here, say there's m, and then all you have to do is the total number of inversions within this entire list is just n plus m plus the number of inversions between these two. So how do you count that value? It's actually pretty straightforward. So say we start at this 3 here, right? This 3 is greater than this 2. That means that those two values are inverted, right? Additionally, that means this 2 is not only inverted with this 3. Oh, sorry, completely forgot. Sort the arrays. Yes, start by sorting both arrays. Sorry, because that just makes computation a whole lot easier. And that means that this is like n log n per iteration, but that's fine. So like I was saying, this 3 is greater than this 2, which means that the 3 is inverted with the 2. But because everything past the 3 is greater than it, that means that the 7 is also inverted with the 2. The 10 is, the 14 is, the 18 is. So because we know the 3 is inverted with the 2, we know there's 5 inversions total that have like an issue with the 2. So now the 7, or we can move on to like the 7. The 7 does not have a issue with this 11. They're like in proper order. The 10 is fine. The 10 is before the 11, which is correct. This 14, the 14 is not properly placed because it's greater than the 11. And likewise, because 18 is greater than the 14, to the right, we also know that the 18 is like inverted with respect to the 11. So here we know that there are 2 inversions with regards to 11. And here, because you could see like the 2, we detected that 11 at the 3. And since there were 5 elements remaining, we knew all 5 conflicted with this 2. And at this 11, we detected it at this 14. So the 2 remaining elements conflicted with the 11. So then we can continue. The 16 is fine with the 14. The 16 does conflict with the 18, which means 1 inversion, and then nothing else conflicts. So we would have 8 inversions total between the 2 lists. So that's how we count the inversions. And you can see that the actual like finding the values in between, that is linear time. Yeah. Yeah, sorry. Might have not explained this as well as I should have. So an inversion happens. You have to say you have 2 numbers, A and B. An inversion happens when the index of A is less than the index of B. So it comes before it in the list. But the value of A is greater than the value of B. So here we take these as like this is the order. So like this is index 0 on a list, or sorry, this is index 0 on a list. This is index 1, 2, 3, 4, 5, 6, 7, 8, whatever. Or I guess it doesn't even really matter because here's everything on the left side of the array. Here's everything on the right side. Yeah, exactly. Just like in merge sort, where you like you split them and like this is everything on the right side, this is everything on the left side. It's kind of similar. So if this is like left, then or sorry, if this is like yeah, if this is like greater than like these values on the right side, we know that's out of place because that's like how they are in the final array or how in the original array rather. Because this, yeah. So essentially, yeah, you iterate through and you kind of like go here this way and add the amount remaining when you find like a conflict. Mhm. Yeah, I think it's not like, don't get yourself too confused because I think if there's like a 20 and then like a 5 and a 5, you could say like, oh, you could invert these two, but I think there's actually like two inversions. Um, it's not just like a flip, but might as well be, yeah. My handwriting is horrible, Jesus. But yeah, I'm just saying like, it's not necessarily equivalent with just like a flip. Although I guess you could flip these two and then, yeah. Mhm. Mhm. Yeah, yeah, yeah. Mhm, mhm. From A, yeah, good question. So let me check. Discord, inversion counting is my favorite. Tony, don't make fun of me. I can kick you out of the meeting. Oh my God. Is it only linear if that has, yes, exactly. This was misleading. I'm so sorry, you guys. The actual like combining or the finding the number of iterations between the two halves is linear. The sorting, not linear. The like whole divide and conquer thing, not linear. Getting back to your question. Because this is divide and conquer, this is like original, say this is like kind of only one step of many. So we start with like an original array of 10 elements, and then we split them into halves. And then we split them into like, 3 and 2, perhaps. And then here we would like split into like 2 and 1, and then 1 and 1. So obviously this is like n log n total. But, or would it be like n log n? Yeah, within each level. But I digress. Basically, like I said before, you're going to come in to this step knowing how many inversions are in each subarray. So like this, like I presented earlier as n and m. What you just have to return is n plus m plus the number of inversions between these two arrays. So that's why you uh, want this kind of like way of doing it. Mhm. Right. If you're doing a merge, yeah. Right. Yeah. I guess, yeah, if you're doing a merge, then it doesn't matter. True. True. Okay. Let's move on. Okay. Quick sort. This is like a big one. If you don't already know, quick sort is when you choose a random pivot from the starting array. Then you take that pivot, you separate based on that pivot, all elements of the array, you separate into 3 groups. Values smaller than that pivot, which is here, values equal to that pivot here, and values greater than that pivot. Because the aim of the algorithm is to sort, we know this middle one's always sorted. So real quick, if he ever asks, if you have an array of like all the same element, why am I drawing like this? So if it's like all ones, the way he's presented it is you have this middle group. So after you choose your pivot, like this one, and they all get grouped together in the middle group, the algorithm's done executing. Like it knows it's sorted already. So if it's if all the values are the same, it's going to be like O of n execution. Because everything's in the middle thing, that middle thing is already sorted. But what if that doesn't happen? For these left and right ones, you then choose another pivot. You divide around that pivot, just like we did, so on and so forth. Just like the middle array is always already sorted, values of length 1 are already sorted, just like in merge sort. So then you just move back up from there. Just combine the array together. Proof of correctness. I probably don't know exactly what you want to bring class, but I mean, I think it's pretty straightforward. Like if you can have this half of the array sorted, and you can have this half of the array sorted, then you can take everything that's less than a value sorted, take everything that's greater than a value sorted, and then the value itself, bam, that's your complete sorted array. And I assume if you do have to like prove this, you would use like induction, because you have like this, how he presents it, like k minus 1 step, where you like are assuming that this is already sorted, and then using the fact that these are already sorted, you can combine them together to get this total array that is also sorted, thereby proving the induction. Yeah, I don't think it's super unintuitive. Just like if the subsections are sorted and you throw them together, the whole thing's gonna be sorted. Yes. Average case. Yes. Yes. And we'll go over why that is and why that n log n sometimes isn't. So first of all, the n component is pretty straightforward. You can kind of look at it like this is the n component, right? You're always going to be iterating like over all n elements of the array, right? This one's accounted for. Then you take like these ones and you split these up, and then you split like these up, and so on and so forth. So you're essentially looking at every element of the array and like pivoting like around, like saying like, oh, 6 is here, -4 is here, 5 is here. That's all n time, right? So every single iteration, pivoting around that pivot is O of n time, because you have to like take the ones that are greater, throw them on the right side, take the ones that are less, throw them on the left side. That's all n time. And because you're splitting this in half every time, it's going to be log n total on average times you have to do this n operation. Yeah. Yes. Mhm. Yeah, should we go back to merge sort? So yeah, okay, yeah, merge sort I did say always n log n. Yeah. And I would recommend, honestly, like if you can understand why these things are the case, that's so much like easier in my eyes than having to like remember it. Because if he gives you like a totally new problem, like know why these are n squared or n log n. But yeah, if everything is the same, they all get put in this middle section, which is already sorted. So it runs once. Pretty much this log n factor is completely negated, right? This only runs once and then it's done, which means it's n time total. Now, if they're in order, and okay, before we discuss that, let's discuss the worst case. So quicksort is n squared worst case, as opposed to merge sort, which is n log n worst case. Why? Take a look at this iteration here. No, I'm lying. Take a look at this iteration here. What happens here is we choose -4 as a pivot. And what's significant about this pivot is every single element in this array is greater than it, right? So instead of being able to split the array in half like we did in here, we only subtract one element. And splitting it in half is what gives it that log n time complexity, right? If you have this array and you like are able to split it in half, half again, and half again, it very quickly, it's like it only takes like a logarithmic amount of steps to just reduce it to one element, where that's just log complexity total. However, if instead you're only erasing one element, so like in this case, right? You're running on like if you start with n elements, all you can do is just like eliminate this one element, and then you're running it again on n minus one elements, which means that instead of being able to like half, uh, you then have to run, this is what, 9 elements total? You then have to run on like 8, and then 7, and then 6, and then 5, and then 4, and then 3, and then 2, and then 1, which is n operations with like a cost of n for each, which leads to that n squared total complexity. So instead of being able to continuously half that array, you just do it with like one less element every single time, which is just like n times total. Yes, so that is the worst case. One place where that worst case will crop up might be where they're sorted. So if you have an algorithm, I guess this is kind of difficult to define a worst case. Yeah, right. But like the worst pivot, let's take an example. Yeah, if it's randomized, how are you really going to know? So here's a situation where it would be that n squared. So if it's sorted and you're taking your pivot element is the first element every time. So like here it would be 7, which would be kind of bad because that's the greatest element in the array. But what that means here is that like you select this 1 out, you iterate with the rest of the values. You select this 2 out, you iterate with the rest of the values. The 3 out, rest of the values. 4 out, rest of the values. So by itself, if pivot selection is random, it's difficult to like pinpoint like, oh, this will be n squared. But if the pivot is something like selecting the first element and it's ordered, that will be like guaranteed n squared. Because the pivot you want is always from the middle of the array. Not like middle in terms of position, middle in terms of value. Median, you say? We'll get to that. Okay, do we have any questions here or moving on? Alexia, what were you? Questions on space complexity? I don't think so. Yeah, quicksort is log n. You were completely right. N log n worst or n squared worst case right now. Sorry, what were you asking? Oh, okay. Yeah, you're talking about like the crazy math proofs. Yeah, don't worry about those. Like he said during the review, like he doesn't teach this course to like prove the math. It's more so for like the algorithms. Yeah, so don't worry about it. Like know why this is like n squared worst case or like n log n average case, but like don't worry about like the math, like the log math or whatever. I don't think we have to know that. Okay, let's move on. So then we have quicksort's little brother, quick select. And this one's kind of cool. So the problem statement is to find the kth smallest element or kth largest element, whatever, the position of like a value in the array. So say here we want the second to last. It said here, second to last element, which we know would obviously be the 6. How would we do this with the code efficiently? So we can actually do this in linear time using this algorithm, average case. If we take a pivot, this 2, for instance, and then we partition around the pivot, which is n time, we can then, we know that like, how many elements are like greater than this 2 or less than this 2? There's 4 elements less than the 2. And there's 1 element that is the 2, and there are 4 elements greater than the 2. If we want the second to last element, we know that's going to fall within, or that's going to be element 8, right? So element 8, we're looking for element 8. Element 8 does not fall within any of these, so we just cross these out. We're done with those. Then we choose a pivot from the part of the array where the kth smallest element is in, or second to last element in this case is in. We place that down. We partition again. So here we know this is like the, geez, there's 4 here, there's 1 here, so there's like 5 on here. And then this is like the 6th element would be here, the 7th element is here. The 8th and 9th element, 8th and 9th element are here. So we only continue with this, and then we would choose like 6 as a pivot, and we'd find it here. So basically, the overarching idea for this algorithm is basically using the pivots, we can determine how many numbers are less than that pivot and greater than the pivot. And once we have that, if we know like our kth to last element is, if we know like there's 2 in here, we know the kth to last has to be in here. If we know there's like 1 in here, we know it can't be in here, and so we can cross that out. Make sense? And then the distinction here is, why is this linear versus this, which is quadratic? Or not, this is like log linear. Well, here we only recur in one array. And so what that basically means is, average case, we start with like this n, and then instead of going like this, where we like split every time, and it's still like, you can kind of visualize it, like this is all n. You have like this full array, and then you only compute half, and then half, and then half again. And this is just like some math stuff. Basically, this will never like be greater than 2n, kind of, but it's linear. Yeah, yeah. Yeah, yeah. Mhm. Right. So like, yeah, exactly. So instead of having like this log multiplier, which you would if you did both sides, you have a constant multiplier. Uh, Average case. You can imagine worst case isn't much better than that of quick sort, because you have like just n minus 1 over and over again. It's literally the same exact thing as like the quick sort, where you like have to do this iteration like n times or n minus 1 times, and then it's just n squared. For now. Why? For now. Median of medians. This is like, I feel like by far the most confusing thing in this chapter. And that's this is like button thing. And that's just because like it's such a, there's so many like weird constant things in it, and like the way the time complexity is calculated is like really confusing and stuff. But I think like we're here to teach you, or I'm here to teach you like what you need to know. Yes, you hate median of medians. You hate moms. So true. Look at that like smiley. Oh, it's gone. Sorry, I've distracted myself. Okay, basically, what this allows us to do in a very broad sense is it reduces the worst case of the quick select from n squared down to n, O of n. And it reduces the worst time complexity of this quick sort back down to the average case of n log n. The math there is complicated, and I'm gonna be real, I don't understand it, but I don't think it matters. It shouldn't matter, because like all you have to know is that like it makes this stuff linear or log linear. And then the overview of the algorithm, right? So say you have like all these values, right? They don't have to be ordered. What you do is you split them into groups of 5. You take the median of all of those values, right? And then you can just keep doing that over and over and over again. So then you have like this group, and you would split this into groups of 5, and you would take the median of those groups, and so on and so forth. And then, you know, eventually you would come up with like such a small group that you can just calculate the median by yourself. And so this is actually like a really fast way of doing it like by itself. So fast, in fact, that you can combine it with like the quick select algorithms and like shove it to O of n worst time. And that's because like, you know, you have like a full list of elements you iterate over, and then you iterate only on like n over 5 of those, and then like, oh, it's 25 or whatever. So this is like log base 5 instead of log base 2. So it's very, very quick. What was I gonna say? And then the actual like goal of it is we want to have a pivot that is, I think, within 7/10 of one side of the array. So essentially like you'd want it to be decently close to the median. I think the exact value is like you want 7/10 of the values, no more than 7/10 of the values on one side. Because again, what was the worst case was caused by like selecting a pivot that was like right on the edge, because then all you could do was just rerun the algorithm on like a very large part of the array. With here, it's enough of a split where like the 2 sub arrays you have to run on like are like small enough where it will like go into like logarithmic or O of n time complexity. And so the way this is kind of accomplished is here in this diagram, you can see like, here's the final like computed median. These are all values that are less than the median, and these are all values that are greater than the median. So we can essentially just eliminate like these huge swaths of values that are like too large to be the median and too small to be the median, like for every recursion, or for like every time we recur. Because basically like, okay, if this is greater than like the values here, and then this is greater than like the values here, we know that all of these have to be less than the median. And like if this is less than this, like this is less than this, and then this is also less than that, and so on and so forth. Which just basically allows us to trim the array down very quickly. So it makes quick sort worst time. No, quick select, other way around. I hope I didn't say that the other way around. Quick select becomes O of n, and quick sort becomes n log n. So essentially, and Tony's got this. They become like their worst cases get capped to their average cases. What about it? Like what? Yeah. So if you ever have a pivot, yeah. So if you ever have like the pivot that is just like instead of chopping in half or whatever, it like chops only a small portion off. That's where you approach the worst case. But then that's why this median of medians is so good. It's because you guarantee a value that is near the middle, like near enough to the middle, where you like where they get small enough, where it'll be like the worst case isn't that big. So like doing this calculation becomes like worth it in the long run. If you like add the time complexities together or whatever, it does end up faster. And it just prevents the worst case, or caps the worst case. Okay, do we have any questions before we move on to DP? Mhm. Yes, so that's I think that was what was presented. And yeah, it's basically it does not improve the best case of an algorithm. And because quicksort best case is n log n, you can't get much lower than that with like a comparison based sort. It sorry. Uh, yes. Yes, sorry. Apologies. Uh, Here. Yeah. Let me like draw this out for you. So um we can say like best case, what if they're all the same element, right? So like we have an array of all twos and we want to find the median. We're using quick select to find the median. What we do is we take a pivot, this two, and then we still have to partition the array, which is saying like, okay, this is equal, this is equal, this is equal, this is equal. So it's still O of n. There's no way to avoid that. Like, yeah, for any like, and it does make sense. Like for anything where you have to compare out of the entire array, like you have to check every element in the entire array. There's no way to avoid that. And I think, don't feel bad. I think that was one of the mistakes like he made on the quiz when he was grading it. So it is O of n. And yeah, like you said, median of medians only serves to improve the worst case. It does not improve the best case. Quick sort, Olivia. Yes. Quick select. Yes. Quick select is already O of n. Why use it? Good question. So quick select, although it's O of n average case, it can run into a similar problem as like with quick sort. So if you choose a bad pivot and you still have to iterate over like effectively the entire array, you might have to end up doing like n or n minus 1 iterations. Essentially, it'll be like of complexity n, which leads to an n squared worst case. So it's not about the average case, it's about the worst case. So quick select may be O of n average, but it's n squared worst. So we want to minimize that worst case, and that's what median of medians allows us to do by guaranteeing that O of n worst case. Okay, Let's move on to DP. No, not yet. Let's move on to DP. Okay. First question, weighted interval scheduling. So the, I guess, background on this problem is you have like all these intervals, and the intervals may overlap with each other. They have a start time and an end time. We kind of know this with like the greedy unit. We had something similar, and they each have a weight. And we want to find the subset that has the greatest weight. How do we do that? Well, first thing we do is sort by finish time. So like in this case, this would be like index 0 and then index 1 and then index 2 and 3, 4, 5, 6. And then what we would do is we would pre-compute a value, which basically said, if I took this interval, interval A, what is the first interval that I could take after taking this value? And yeah, so it's basically the earliest available interval after that. So, and this is what this p-value is referring to. So after index A, I can't take B, C, D, E, or F. I can only take G. That's correct, right? The first one that's not obtainable. Okay, yes, that would actually make sense in hindsight, right? Because that would like use this ending value, right? Would it? Yeah. Yes, he did do it like that. Yes. Yes, yes. Okay. Yes, sorry. That makes more sense. Yeah. So this H here, yeah. Yeah. So you look at the start time, which is like 8 here, and you say, because we have them ordered by finish time, yeah, this is what you should be doing. Sorry. You basically say like, okay, I can't take this interval that ends at like, that's index 6 in this ending array, or the one that ends in 5, but I can't take the index 4, which means that indices like 0 through 4 in that array, I can take, and then like 5 and 6 I would have to discard if I took 7. And so that's what that P of J values was used for. Everyone good with that? If the list is sorted, quick select and quick sort wouldn't change. You can't really know because of the fact that the pivot is randomly taken. There's some things like if the pivot is the first value, if the pivot taken is like the first value, then technically they would like always be in their worst case. But that's like not really like if you're choosing a random value, there's no way of knowing. Oh, you're saying, okay, if you're saying if they wouldn't change because the worst case is capped, if it's using a median of medians approach, yeah, then it wouldn't change because it was at like the worst case is capped. Why would this be O of n instead of O log n or something with log n? Alexia, are you asking about quick select? Oh yeah, this is, yes, okay, this is so yeah, this is because you're binary searching, this is n log n. This is, sorry, yeah, I'm talking about, yeah, this O of n is not referring to the overall like computation, it's referring to like this dynamic programming relation. So computing like the actual thing. If all elements are the same, what's quick select time complexity? I was going down the chart. That would be O of n. Yeah, if they're the same, the quick sort and quick select are O of n. Anyways, yeah, ignore this line for now. So basically what you're doing is you're doing a binary search for like this one, you're saying, oh, okay, I can only take intervals before interval 4. And then like here, you're like, okay, what is the cutoff? I can only take intervals before interval 2. That is your P of J value. Basically saying, if I take this interval, which ones can I keep taking and which ones are excluded from me? Which kind of like goes into that DP idea of like, okay, I make a choice. What do I do now that I've made that? What can I do now that I've made that choice? And yes, because you're binary searching for every single interval, this pre-computation is n log n. So the overall algorithm is n log n. But then what these P of J values allow you to do is do this Bellman equation. If they allow you to run DP in like O of n time. And so what this recurrence relation is saying is saying like, okay, if I am here and I choose to take this interval, I want to take the maximum, like I have a choice to make here, and I want to choose the decision that maximizes my outcome. I have two choices. I can either take this interval and then continue from here, right? Or I can skip this interval and continue from here. So what that manifests itself as is this, where like here, if you took h, you would say, you would have like 3 to your total value plus the optimal value from D onwards, which I think we said, and this is like optimal from PJ. I think we said like D is what, like 3, 4, something like that. Or you could skip. So I don't know. I can't remember what this was. Opt 8 would be like opt 7. So basically what you're doing here is you're saying, I want to either skip the interval and just move to the next interval, or I want to take the interval, collect its weight, and then take the optimal of every other interval I can take now that I've taken that interval. And so this can actually just be done in linear time because of the fact that that there's only n possible like states in this array where you ever have to compute opt at. And so if you're able to compute opt at every single one, you'd never have to do the opt computation again. So there's only n total computations of opt, and it's just linear time to compute each opt calculation. And then this is just saying like, okay, if I'm here, just return 0. There's no other intervals to take, so my optimum is here, 0 here. Can you read the last question on the quiz? Remind me later. After I do this, I will review, or we can talk about those questions. It's okay. Does this make sense? The DP, I think, is not super duper intuitive at first, but hopefully it'll make more sense as we move forward. Here, what this basically boils down to is you're given a choice. I think this part should be kind of intuitive. At any interval, you're given a choice. You can either skip the interval, move on to the next one, or take the interval and then move on to the next one that you can take after taking that one. And that's just what this is doing. Okay, so then next, yeah. What? Yeah, so effectively, yes. Like maybe if it's top down, it might not or something like that, but yes, it probably will. Yes, yeah. Like in knapsack, it might not, but here it's definitely would. So yeah, essentially if you started at this like time 11, this would call like time 10, time 9, time 8, time 7, so on and so forth. J is job index. Yes. Yeah. Yeah, that's correct. Sorry. But it would basically do it at every single job index, which is why this is O of n. And the reason this isn't higher is because once you've computed like, say like the value, like the most optimal value at this point, if like this refers to here and like this refers to here, you would still be returning, you would have this value you'd have like written down, you'd have memoized. And so you could just like fetch it. And so you only have to, the bottom line is for every interval, you only have to compute like that value once for every like value of j. And so basically it would be like O of n. Does that make sense? No. Memoizing is very much something like it's just something you kind of do in code. Because yeah, like, and he's probably going to give you this, like maybe he'll make you like derive one of these, but the memoization itself, it's kind of, you can kind of just say like, okay, I'm memoizing this, and that will like make this more efficient. It's basically just like a way of making the recursion more efficient, but that's kind of just something you have to worry about, like if you're actually writing the code. I think here there's no intricacies there. I don't know. Will this be posted? Yes, I'll post it. Is it still overlog n log n? Yes, yes. And yeah, so this is this sorting part's n log n, this binary searching part is n log n, even if this is O of n, the whole thing is n log n. Okay, let's move on. Max continuous subarray. So say you have a range of numbers. So here would be like 3, -1, 4. No, is that what this is? Yes, yes. 1 and 7. Is this? No, it's just this. So say you have like these 4 numbers, and you want to find the maximum chunk. So a contiguous subarray, which is basically saying the elements all have to be like in one block; they can't be split apart. Where the overall value is the greatest. And so the way you do this is for every number, you choose to either just take that number or take that number and the most optimal way of taking the previous number. So you either take just that number or you take the previous number and every thing that's optimal to pair with the previous number. So for this example, right? When we choose to take, we're obviously going to take the first number because it's a positive value. We just want it, and there's no way of not taking it. So for this -1, we can either just, so this is going to be like our max, like our opt table here. So we can either just take this -1, or we can take this -1 plus the optimal value of the previous index, which is essentially saying, let me take this value in conjunction with everything I took in the previous index. So here this would be adding the 2, it would be 2. When you take this 4, you could either just take the 4, so just chunk the 4 out, or you could take the 4 plus whatever you took in the last one. So that would be the total interval. And then you could just add, 4 plus 2, 6, which is the total thing. When you take this 1, you could either just take the 1, or you could take the 1 plus this entire space we previously calculated, which would be 7. And then when we, the important thing is after you compute this opt table, the max continuous subarray, since each of these each of these are representing the optimal value for a subarray ending at that index, you have to take the max out of all of these values, which in this case would be 7. It's not always the last one. So essentially, with a list of numbers, you either choose to take a number just by itself, or take a number plus the cumulative sum of the optimal array ending in the previous element. Does that make sense? You mean this? Or okay. There might, yeah, okay. I can actually, let me 3 -1 4 1. Yeah, I just tried that, but let me try rewriting it here. 3 -1 4 1. You want a more complicated example? We can do a more complicated example. So I'm thinking one where maybe the last element isn't the best to take. So because this only goes over one case. So say we start with a 3. Let's do this one. Right. So let's have this kind of table of optimal values. And what this opt means is this is the optimal, the greatest sum of the contiguous subarray ending at that index. So for this index 0, we can choose to either or we all have to take the 3, and there's no other choice to take before that. So the optimal value of a sum ending at that index is a 3. With this -5, we can choose to just take the -5, right? We have 2 options at this point. Take the -5 that end at this index. Take the -5 or take the 3 and the -5. This has total value -2. This is total value -5. So we prefer the -2. We'll take the -2. This is where the DP comes into play. or like the choice comes into play. So 3, -5, 4. When we take this 4, we can choose to just take the 4, or take the 4 plus the -5, or the 4 plus the -5 plus the -3. Now, all this is what we already computed in the previous step. So that's this -2 here. Like the maximum between these two elements is just the -2 here. And so that's this this value we have here. So we're essentially saying between these two, the max of these two is the maximum value that ends at that index, or the maximum like sum of a subarray that ends at that index. But we're presented with like a new choice here, and that's just to take the 4. Now in this case, we know that like the optimal thing here is just to take the -2, and we'd be adding the -4 to that, but that would still be like 2 if we summed up all of these values. So what we do here is we just choose to take the 4 by itself, just this outcome. So here we don't want to pair it up with the optimal like last array because it's negative. And then this -2, what we do is we'd want to group it with this 4 because we could just take it by itself, which would be -2, bad, or we could add it with the previous optimal value, which previous optimal value is just for itself. So we group it with that, and we get a total value of 2 here. And then when we iterate over this, we don't just like select this. We look at all of them and see what's the greatest, which is this 4 here. And so what this is representing is in the original array, just taking this 4. -2. And you can see that like with this 4, we don't want to go like backwards because that would mean stepping into this negative, and then you're never gonna be able to make a greater sum. And you can't step like forwards because you would step into this negative and diminish your sum. So that's what this is kind of doing by just deciding to like, okay, I'm not gonna bother because even every best case here is worse than what it is here. And like if, yeah. So okay, yeah, finding out what the actual subarray was, what the actual subarray is. Yeah. And in this problem, it's pretty straightforward because like at this max value, you know, it like includes this third element, right? So you would know like 3, 5, 4, -2, 3, 5, 4, -2. You would know it like includes this value. And then since like the optimal value is like 4, you're just done. If the optimal value was like 2, you could like work backwards and you could be like, keep taking values until their sum is equal to like -2. So that's how you would trace back here. But I don't think that would matter, or that's going to be S. Okay, I'm going to move on. Unless anyone has any questions. Knapsack, this one's important because presumably there's an FRQ here. Ignore this little thing I wrote. I don't think this is actually important. Okay, so the problem statement here is you have a bunch of items, they have a value, and they have a weight. Given a limit of weight, you want to calculate the maximum amount of value you can store in that weight. Let's go over the table of the recurrence relation. Let's do the recurrence relation. So how we do this is we store in this like optimal thing, we say for a given index and a given weight. So given that I can carry a certain weight, what objects of like, or what subset of items like this index in prior will I be able to like take for optimal outcome? So obviously if I equals 0, that means you can't take any more items. And all of these are just 0 because there's no like values to be had. And then what you can do is, shoot, I don't actually have like the table of items here, which is kind of sucks. But basically what you can do otherwise, given an item, so here it's like item 1, I equals 1, you can choose to either not take the item. So say we're like up here, right? And here like I equals 5. We can choose to not take the item, thereby just going to the I equals 4 case instead. Or we can choose to take the item, adding its weight to our total, but also subtracting adding its value to our total, but also subtracting our weight from what we can carry. So that's represented here, right? Here, we have this value of 40. And what we choose to do, we have a weight limit of 11. What we choose to do is to take this item, which gives us a what, like 22, like 22 point increase. But since this item weighs 6 pounds, we have to jump over to this value in the table. So what like this is basically calculating in this case is saying, is it more optimal to not take this item, which would give us 25 points over these 3 items with 11 storage capacity? Or is it more valuable to take the item, which would yield us 18 points over these 3 items with only 5 storage capacity, but it also gives us this 22 from the item? And what we find is that adding the remaining like problem with only 5 spaces and adding the 22 is more useful than skipping the item and only getting 25. And then this is just saying like, okay, if I can't take the item, just skip it. Like if the weight of the item is larger than like what we can carry, just skip it. I don't think base cases are going to be terribly important to worry about in this case, yeah. So yeah, traceback. Traceback is going to be difficult to display here because of the fact that I don't have the item weights, but I can kind of show this off. Yeah, it's going to be raw. So I think it's kind of like what I showed here. We want to know at any step of the iteration, like what did I choose to do? So like here we know I could have not taken the item, and I could have taken the item, jumped back here, and like gained 22. So because this value is greater, because this 22 plus 18 yields us this 40, we know we jumped back and we took that item, right? We reduced our weight from 11 to 5. So item 4 must have been taken. So we know like in our results, item 4 is like what we took. Here, 18, this is what? This is value 18. So there's item 3 is value 18. And if we jump back, it's also weight 5. This is weight 5 and value 18. If we jump back 18 or 5 units, we can see that there's like the optimal thing of these two is just 0. So we know the optimal outcome here is, or for taking it is just getting the 18 here. But if we don't take it, the optimal outcome is just to have 7. And since the 18 is greater, we know we must have taken this item as well. So item 3 also was taken. Does that also make sense? Yes. Mm-hmm. Yeah. Yeah. The recurrence relations are like, even when you're programming and stuff, like that's the rough part. And I think he might give us them on the exam. Like I think he said like some problems he does. But Mhm. Yes, exactly. Because at the end of the day, like it's just like a recurrence tree. And what it comes down to is like you have a choice to make. And with a lot of these, it's like take something or don't take it. And you want to like maximize your outcome. Okay, try not taking it, see what your best value is, or try taking it and seeing what your best value is, and then just do what's better, right? These two are just like when you don't have the choice and you either have to like, you're either like forced to skip or you just stop iterating. But at the end of the day, it's like, what at every step of the program, like what is the choice I'm making? And then just represent that in terms of like these smaller problems. Any idea? How do we prove the optimal substructure property with the exchange argument like he was talking about in the review? I don't think I know what you are referring to. I'm gonna be real. Sai, do you have any idea? Mhm. Okay. Yeah. Mhm. We can look. Yeah, so okay, we can look at that after this then. Actually, we can just do it now. The last question on the quiz about weighted interval scheduling. It was no, sorry. We just finished the slides. There, I think we only have like, yeah, we're pretty much done. We'll do that first. Sorry, I'm jumping all around the place. And then format, don't know. He said there was going to be like a knapsack variation. So I listed some earlier, just like adding an extra parameter, trying to get a certain weight or a certain value. But I would just say like understand why this recurrence relation makes sense. I can't draw anymore. Oh, it's because I don't have a pen. And then you should be okay. Okay. Sequence alignment. This one's a little funny. So basically, given two strings, you want to get and given like a gap cost and a like mismatch cost, determine how you can like align them to minimize your like cost. And so here you're kind of minimizing instead of maximizing. And so basically, we'll just try and understand this recurrence relation. I don't have like an example for this one or anything, but basically, if there are no, if like I equals 0, that means there's like nothing left in like one array. That means you just have to take like the number remaining gap cost for the other array, and it's the same thing here. And then this is basically saying, okay, at a certain element, we can choose to match the two values, which would like give us this mismatch cost. And then we continue optimal on the remaining values. Or we can choose to like take one of the values and then like make a gap and then take the optimal of the remaining ones, or just like take a gap from the other one. So it's basically just like, okay, I have to choose like at least one value at any point to take. I can either take a value from one array and then like not take one from the other array, which will gap. This works in both ways. And then, or you could just choose to take values from both arrays, like match them up and then move on with your life. I'm kind of trying to go a little faster here. What is this one? Longest common subsequence. Okay. Yeah. All right. Okay, yeah, this is similar. Yeah. So basically this is saying if you have like, I don't know, numbers or letters, what's the like longest common subsequence between the two? And this does just kind of map into like you can't mismatch, you can only gap. And subsequence means non-adjacent. So if you have like a I don't know, frogs and like logs, that's a terrible example. Whatever. The idea is you can like take non-adjacent elements, so like match with like fog. And so what you do here is you say, okay, say you have two words and you have like an I and a J index. If they're equal, that's perfect. You can match them up and then move on. Or just like in the last one, you can choose to move I back, or I guess you're moving backwards in this case, and keep J the same, and then incur like that like penalty, or like it's just not common. Sorry, it's not a penalty. You're trying to like maximize. Or you could choose to like move this one back and keep this one the same. But yeah, when they're the same, you can also try matching them up and then moving them both back. Yeah, but it's also this for reasons that like make sense because you can't mismatch in this case. It's only the common values. Okay, still going forward. Okay. Um, this is a shortest path algorithm that works for negative edges with negative weights. What it does is it basically, we start like here and we maintain a list of like shortest path values, um, or like a distance value for every node. And what we do is um, we basically say like, okay, this is adjacent, and this is adjacent. We can like update this and update this. And then these two were updated in the last one. So now we like look at these ones and we say, okay, we'll update all edges coming out of this node. This one now is like 2 plus 2, which is 4. This one now is 4 plus 2, which is 6. And then but we take this one. So yeah. And then this one is 3 plus 2, which is sorry, I was rushing. That is my bad. Good catch. So yeah, and then here, this node was updated, but it has no edges coming out of it, so it doesn't do anything. This node was updated, so it has an edge coming into here, which then updates this to a 2. And then next iteration, this was updated, so we check this, and we don't do anything. So basically, the premise of it is maintain distances from the source to all nodes. Every edge, every iteration, we relax the edges coming out of all of the nodes we changed in the previous iteration. And we do this n-1 times. So like we start with this one changed, and then we update the distances with these edges. And if that changes anything, we update with all the nodes that were changed, we update off of all of their edges, and we update so on and so forth. And we only do this n-1 times. Because if you think about it, the like longest possible path to like a node can only be like n-1 edges. Like if you have a node way over here, like on the other side of a graph or whatever, there can only be n-1 edges like between the two. Like the shortest path is like capped by that. Yes. So the idea is, or the issue is negative cycles. So let's say that we have like, let's say we have like a negative cycle here. So this is like -3 weight, -3 weight, -3 weight, and then we can have this coming in. This is like the source, edge weight 2. Say we're running the algorithm. What it would do is it would assign this like a weight of 2, and then it would be like, okay, let's relax this one's edges. So it goes here. Oh, this is distance -1, and then we'll say, okay, let's relax this one's edges. Okay, this is distance -4. Okay, let's relax this one's edges. Okay, this one is -7, so this updates this. This is now -7 distance away from the source. Let's update this one. Oh, look, this is -10 away. Oh, look, this is -13 away. Oh, look, let's do it again. So that's the issue. It just goes into this endless loop. And that's why we only run it n-1 times. Because when we only run it n-1 times, like it only has the capability of going around 1, 2, 3 times, and then it stops. And then that is how we can actually use it to find negative cycles. Because if we, go back to our original scenario here, right, where this was like 2. If we run this 1, 2, 3 times, we then have like values to the shortest path for each node. If we run it again, the nth time, so if we run Bellman-Ford n times, this would update to like be like a negative, I don't know, what was it? Like -5. So on the nth iteration of Bellman-Ford, values will only update if there's a negative cycle. And that's how we can check if there is a negative cycle. And then like finding that cycle, we just like look at the value that's changed and we trace it back to find the cycle. It's not terribly complex or unintuitive, but yeah, basically because you only need n-1 iterations to like reach each node, if there's ever a node that's updated on the nth iteration, you know that there's been a cycle and something's getting re-updated. Okay, network flow. For detecting a negative cycle, I'm pretty sure that's all it is. And I guess I would know like how to trace it back. And here it's just like you look at the node that was updated, and then you can like work backwards because you're going to be storing like in Bellman Ford, it just stores successors or predecessors rather. So you know this one's been updated by this node, and this node's been updated by this node, and this node's been updated by that node. And when you just like work backwards through that, you see that like this node pops up twice, and then, so this is the cycle. But yeah, detecting them, run Bellman Ford like n iteration. Source. Yeah, I think he did it a bit more complicated than it needs to be. Yeah, you don't have to worry about that. Like, the, yeah, yeah. Basically, look at the value that was updated and then just trace back because you know the value that was updated must be part of the cycle. Or I guess it doesn't have to be part of the cycle. But anyway, it like has a predecessor like in the cycle. So if there's like a duplicate value in its predecessor array, you can determine what the cycle is. Is it the last node that updated? That's the cycle. Will the nth node always be in the cycle? Yeah, like, or because like I'm thinking like the negative cycle like will propagate to like other nodes. So like this node would have like negative infinity distance from the source, but I think that would never be the nth. Yeah, yeah, yeah. Mhm. Yeah, yeah. So yeah, yes, yes, yes. Nodes that are updated within the nth iteration aren't always in the cycle, but they will always be succeeded, or they will always be like preceded by the cycle, because otherwise they couldn't have that negative value pumped into them. Mhm. Okay, yeah, I think that's about the definition of Bellman-Ford, because the definition of Bellman-Ford is like on the ith iteration, that is the distance of any shortest path of at most I edges. Is that what you're referring to? Because like here, like iteration one, this is like two and this is four. That's saying like any shortest path of like, and this would be like, I don't know, infinity, I guess. Like these are the shortest paths of like length one or lower. And then like here, this would be second iteration, this would become like four, this would become like seven, and this would become not less than four. So this is like all shortest paths of length two or lower. Oh, yes, yes. And that's because, mhm. And that's because, yeah, because the way I've been, yeah, I should go over that. The way I've been going over it is like only the nodes that are updated within the past iteration actually relax their edges. But what he did is like there's actually a set order of nodes, and like that's an optimization. What I was doing was like the optimized version. There's actually like a set order of nodes that are updated, and every single one of these nodes is updated n minus one times. So what that would effectively look like is like this is the he might ask about like this version. Uh, in fact, this might be like the version he asks about if he asks a question. Uh, so like P gets updated, right? So this becomes like two and this becomes four. And then that means that within the next iteration, you or within the same iteration, you're already updating Q. So like then this becomes four. And then now you're going to S and like that does nothing. But then you're going to R. This does nothing. And then this goes to like seven. And then you update T. And then this goes to like -2. So you actually find everything sorry, you find every single shortest path within just like one iteration with this like combination of nodes. And so that's what it was. It wasn't like edges. It's like um yeah, yeah. Mhm. Yeah, yeah, yeah. But like all the ones that are like of length one, all the shortest paths of length one, which is like this Q and the R, you're guaranteed to find on the preservation. If I had like these backwards, I would probably like these nodes would never iterate. And I would, in fact, like, yeah, these nodes would also never iterate. So all I would do was like, find these two shortest paths. So you're just guaranteed the shortest path with the, like unoptimized version, you're guaranteed just the shortest paths of length I. And yeah, the unoptimized version is probably what he's going to be talking about. It was just, it's a lot. Just know that with that, you update every n nodes, like, yeah, in like a certain order, n-1 times. It's just a bit complicated to explain, I feel like. Okay, network flow. Max flow, I'll start with max flow rather than min cut, because I think the way of actually doing the algorithm is not unstraightforward. This is asterisk because it does, we're doing an FRQ about this, or we have a long response question about this. So I don't know what he would actually ask about this, to be honest. Like it's really just like doing the algorithm, which we've gone over. Could be. Didn't he say he would make like a bonus problem or something? He always says that. But yeah, it might be something conceptual like that. So I do think you should kind of like understand how these work and like why these work. So how this, we'll start with Ford Fulkerson. So this will give us negative flow as long as like edge weights are integers and all that. There was some exceptions you went into, don't worry about them. They're new stuff. So how this works is you find a path. This is like, this was the source, this is the sink. Find a path from the source to the sink. What's the lowest edge weight from this path? It's 2. Before I do this, actually. Every node, so this is the idea of the residual network, right? This edge here from 4 to 6 has capacity 10, which means that from 4 to 6, you can pump 10 units of like flow. From 6 to 4, we say that like there's an edge there with like capacity 0. And when you pump stuff from 4 to 6, so say this is like reduced to 5, or say this is reduced to 2, then this edge here from 6 to 4 would be increased to 8. So if this becomes 2, this will become 8, because you're basically saying now I can pump from 6 back to 4, 8, like a volume of 8. And what that effectively means is like you're just reverting this back to 10. So all the residual network is it's edges running anti-parallel that update when the original edges are updated, that allow you to undo your changes by flowing through them. And that should hopefully become a little more clear when like we walk through this example. So what we would do is we would have like edges with like capacities of zeros running against all the currently existing edges. Oh no. There we go. So the first thing we think the core like cycle of this algorithm is you find a path from the source S to the sink T. So say like this here from 8 to 10. You find the bottleneck. So here it's 2, right? You can pump 8 through here. You can only pump 2 through here. You can pump 10 through here. So that means that you can't pump more than 2 from the source to the sink in this case. So what you'll do is you'll decrease like the capacity of all of these by 2, 0, and then 8. And you've effectively pumped 2 more into the sink. What we'll do with a residual network is we'll then increase all of these by 2. Effectively, we're saying we can pump 2 backwards to restore how they originally were. Let's repeat it. So through this bottom path, our bottleneck is 8. So we can pump, or we'll be left with 2 capacity here, 4 here, and 0 here if we pump 8 through. Likewise, the residual edges would be increased by 8. 8 here, 8 here, and 8 here. So we're essentially saying for each of these edges, we can pump 8 back in the other direction to essentially undo the pumping we did at the start. So if you notice, this edge is like completely saturated, but this one can still take 8 more. Okay, how would we accomplish this? Like we still need another path. For instance, what we could do is we could pump 6 up here, and then maybe some down here, and then back up here, and then back down here, or back through here. So, okay, let's try that. This is 6, this is 7, this is 4, this is 8. So our bottleneck is 4. Let's pump through here. Doink, doink. 3, this becomes 0, and this becomes 4. Again, our residuals are updated. We can pump 4 more through each of these instead. Or it's a very messy diagram right now, I know. 4, and then this becomes a full 6. And notice that like at any point, the residual plus like the amount we can flow through the residual plus the amount we can flow through the original always equal like the original capacity we're given. And that's basically because we can like pump back all of the stuff through the residual to get back to that original capacity. So what do we have at this point? So at this point, we have 8 here and 6 through here. And if you notice, and here's a like interesting thing here. This edge is fully saturated. So coming into T, we want to see, is there any other like way I can flow more into T? This edge is completely saturated, so we can't flow more from here. This edge has room, but anything coming into here, here's a 0, here's a 0. So there's no more room coming into here. So we pretty much know we can't pump any more into the sink because everything else is blocked, essentially. There's no way, there's 0 room to flow into here, 0 room to flow into here, and 0 room to flow into here. Let's mark that off real quick. Now, we can calculate our flow by, for this last lecture, taking like the flow through any cut. Essentially what that means is the easiest way is just to like look at the sink source. How much is going to the source? Oh, there's like 8 here and like 6 here. That's 14 total. Or like you can look here. There's 6 coming this way and 8 coming this way. That's 14 total. So 14 is our max flow as we've computed it here. Let's look at this cut we've made. So if you add up the values coming from this chunk into this chunk, you can see that the total edge weights become 14. Now, min cut, what is this? It essentially says is if you make a cut and you like have 2 groups of nodes, one of which contains S and one of which contains T, the max flow will always be equal to the lowest cut when you sum up all of the edges going from the S group to the T group. So basically, out of all the different cuts, like say I could do this one, which is 12, 7, 2, which 21, means that only 21 flow can flow from like this half of the graph into this half of the graph. Basically, the lowest value of that, which in this case, we've found a cut that's value 14, is the value of the max flow. So that's how we actually know if you ever have to like work through a max flow problem, that's how you can know you've reached the optimal max flow. Because last slide we were thinking, is there any other way I can pump more through this graph? Because of the fact that we've reached a point, or we found a cut, sorry. We found a cut with value 14 and we have a flow with value 14. Because of like the min cut max flow equivalence, there's no way the max flow can go higher because we found a cut that like will undermine that. And yeah, and so the intuition here is if we look on the last slide, this 2 to the 4, the edge is completely saturated. This 5 to the 4, the edge is completely saturated. This 5 to the 6, the edge is completely saturated. So essentially these nodes, there's no other way for any flow to get into these nodes. Like the area inside of that is completely saturated. So min cut is basically, okay, I have this group containing the exit, what if these edges were completely like flown through, right? Uh, in this case, that would be like there's the sum of them is 14. And that's because uh, the flow has to get from like the source to the sink somehow. And it will like always be bottlenecked by these edges at the end of the day. Yeah, does that make sense? I think if you work with a little bit, like it becomes more intuitive. Um, basically, like yeah, there's just no way to flow more. You can see it's kind of like bottlenecked here. There's just no way you can get more flow into these nodes than what's presented by these edges. And that's where kind of the minimum cut occurs. Yeah, exactly. And so, right, exactly. And so like here, like the only paths into this node group are this edge, and this edge, right? And so since there is a zero like for each of them, um, essentially there's no way uh, to get to this node group, we terminate, right? Uh, and so therefore you can determine like this is the min cut because there's like this is the first node group to get essentially like isolated when you're trying to blow the maximum through. How do you mark off which section is the start and which is for the exit? As in where the start, exit starts and ends, if that makes sense. Are you talking about for the cuts? I assume you're talking about for the cuts. In an actual like graph you're running max flow on, you'll be given, I'm not sure what you're asking. I'll say this. You'll be given a source and a sink. So you don't have to worry about like assigning those. You'll be given those. And then as far as the cut set, it's the only thing you have to that like matters there is one of the cuts or one of the groups, you have to like cut along the edges uh, such that like, and one of the groups will always contain the sink and one of them will always contain the source. So there's no like, that's just how it works. Uh, and then the edges from the source to the sink, that is the like flow of that cut. Exactly. Yes. Yes. Yeah. So here you would include the 7, the 12 for 19, and the 10 for 29 total. You do not include the 4. Yeah. No, I don't think so. Like the actual like theorem itself, the proof, we did not. But I would say, since we know Ford Fulkerson, I think it's super important to know like max flow is equal to min cut, because if you have something like this where you want to run Ford Fulkerson through the graph, you can check your work like just like this by verifying the cut. Because if you found the cut and it's like the value of your max flow, you know you're done. Like you know there's no other way to push more through the graph. Or if you find any cut that's equal to your max flow, like you're done. Yeah, yeah. I I feel like he wouldn't do that. That's pretty devious. I mean, at the end of the day, it would be something like this, where like um at a certain point, like an edges to a certain group is so saturated you can't pump any more flow into that group. And you can kind of like verify this by running the algorithm. And that gives you like that is we saw here, like this edge is saturated, this edge is saturated, this edge is saturated, and that is exactly like what our min cut was, yeah. And then that was like summing to 14, which is our max flow. So it's good to know. I don't think, frankly, he's gonna ask like the thing about it. Okay, that's all the slides I have, thankfully. Yeah. So I don't think the example or like the way I did it actually covered it, but the idea of the residual network is it lets you like undo stuff. So like, what does that actually mean? Um, say you, let me like make a custom example here. Mhm. Yeah, yeah, that's essentially exactly what it is. This is this what I'm like thinking of? Um, no, it's not. Circle on the left, the S. Oh, yeah, yeah, yeah. Mhm. Like this. And you mean down? Okay. I, all of the edges as ones? Okay, guys, pretend they're all ones. I'll do it for you. Yes. Mhm. Yeah, yeah. So if you find an edge from S to T and you do this, right? Doomp, 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 right? Uh, Here you've like flowed one into T. You can't do anything else. Like there's no other way to flow. Wait, could you do this? Doomp, 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 doomp. Okay, maybe not in this example. Uh, okay, maybe this example is not perfect. Yes, yes, yes. Okay. So here, if you flow through here and you like add a one to your edge, uh, you can't like the only other way to travel is like here and then you're blocked. Um, so optimally, right, what we would do is we would go like, oh, we can flow up here and then we can flow down here for two. But if we do this flow instead, we need some way to undo this. And this is what our residual networks lets us do. So instead of going uh like flowing, we can flow here, then we can flow here, and then we're able to reverse, or the residual networks reverses the flow here and reverses the flow here. This lets us further take this edge upwards and then take these ones for like a +2 total. So what that ends up doing, if you actually like see what we've done on the graph, we have taken this edge, we've taken this edge, we've taken this edge, taken this edge, and this edge, and then we've taken this edge and gone back on this edge. So what it effectively is, it's just this. So yeah, it just lets us undo flow through edges. Okay. Any random questions? I guess I, yes, sir. Yes. Okay. Um, so that's I can't draw, can I? No. So this is like this thing here. That's essentially like this arrow here or this arrow here. Where here, like you can only take each item once. So you either skip taking the item like this, or you choose to take the item. So here you would take item 4, and then you would be left with like these 3 values to compute, these 3 items to take optimally with this weight. If you didn't do I-1, what would happen is you would like go here, like here, for instance, right? And then you would be like in 1 to 4. So you could take 4 again. So it's kind of just like, yeah, by taking the item, you take it out of the possible pool of items. Does that make sense? Yeah. So you don't want to take an item more than once. So when you take it, you want to say, okay, this is out of the pool of possible items to take. Just like as if you were to skip it. I guess it would be, wouldn't it? Would it? Yeah, I guess it would. I think the way It was presented to us in a previous class I took was in the competitive programming class was you can actually like you instead of like what was it? It was like you could take k copies of an item. Yeah, you don't maximize like not taking it or taking it. You maximize like taking 0 copies, 1 copies, 2 copies, 3 copies, 4 copies, 5 copies. But that's effectively the same thing because here you're just taking like 1 copy and then you could take another copy again and take another copy again and take another copy again. So it would work the same. I think it would be a bit slower, technically speaking, because you wouldn't like compute it all at once, but uh, it's same outcome, yeah. So that would work. Okay, I think someone asked about like the final problem on the practice quiz. Is this? Yes, good call. Okay. Okay. Let me read this real quick. Wait, I can just read it on. So C is asking if your target value, so this is an exact value, essentially shooting for the exact value rather than just meeting a value. This is saying if the value is greater than 0, there's items, each item has a non-zero weight and each item has a non-zero value, then taking this, so this is just asking for what the recurrence relation is, like prove that this recurrence relation is correct. Yes, I remember he did like, I remember him doing this. Yeah, okay. So does everyone like know this is just like so man, I like being able to draw. Well, MS Paint. What the recurrence relation here is saying is basically true. Dude, you're so smart. All right. Okay. This is basically saying for sorry, this knapsack, you solve it. You're saying I want to find the optimal value of given I items. What is the optimal value I can get? Or no, sorry, optimal was like the amount of ways. The amount of ways I can get a certain value while staying under a certain weight. Right? What we do here is it's very similar to normal knapsack. This is not taking the item, and this is taking the item. Right? So what this is doing is it's being like, okay, I can, if I don't take the item, right? Opt I minus 1 VW is the number of ways you can meet V while staying under W of like the items not including I. And then whereas this opt I minus 1 V minus VI W minus WI is saying this is the number of ways with the items not including I can meet value like my V after taking I. So I subtract the value of I from my target value. And then I subtract the value of WI from my target weight. So I essentially emulate taking the item. If I have like, so say like, if I have like, if I'm trying to get like 10 points and I have like a weight of 8 or a storage space of like 8 in my sack, if item I is like worth 5 and costs 5 weight, then you're basically saying, okay, I can take I, but then I just have to find how many ways I can get 5 more points with a weight of 3 in my sack, right? 8 minus 5 and 10 minus 5. So essentially what this is just saying is like, you don't take I, or you take I. And then since this is asking for the total number of ways to meet these two criteria with these I values. You just add the two possibilities together instead of like minimizing or maximizing. I don't know what he's saying, but yeah, it's essentially like with a certain item, there's two ways to like you can either take it or not take it. And then there's a certain like amount of ways to fulfill the condition after not taking it, which is just like same condition just without the item, or a certain number of ways to fulfill the condition after taking it, just saying you're bounded by a different value that is getting rid of that item's value and a different weight that is consuming that item's weight. Yes. Hmm. Hmm. Yeah. Yeah. And you can see uh, um like with a lot of these you're like maximizing. So you're saying like, okay, I want to like minimize over all these possibilities or maximize over all these possibilities. With here you're adding, but it's essentially just the same thing. You're basically just recurring. And whereas in the other thing you would say, oh, I can either take or not take, and I want to take what gives me the best value. You want to say, oh, I could take or I could not take. Like if each of these gives me a certain number of possibilities, the total number of possibilities I have is just adding those two number of sub possibilities. So yeah, I guess not all DP relations have to use that min or max. Sometimes it could just be looking at those subproblems and adding up the results. Is there anything else you guys wanted to discuss with regards to the quizzes or homeworks or something? Last question, second quiz. Oh, oh, ooh. Does it let me view my quiz? Do I have to like open on quiz two? Okay. No, I can scroll. Right, surely. Yeah. Okay. Okay. This one was weird. Uh, yeah, I can go over this one. How do I get rid of these annotations? Trash. Said right click. Okay. Um, I actually like these questions. So okay, weighted interval scheduling. We went over that. And this is saying. Okay. This is saying you have P of I, which is like what we went over. It's the last job that like can be taken if you take a certain job. And then this is just like the same DP relation that we went over in the slides. So this is basically just like you answered. If every pair of jobs overlap, then two n recursive calls are made. So I'll draw out like what I essentially was like writing on my scratch paper at this point. So if all jobs overlap, you have something like this, right? Simplest case. Now this recursive relation, so this is like job one, this is job two, this is job three, this is job four. This recursive relation basically says skip this job, which does something like this. Oh, and this was before we learned about DP. Okay, yeah, he said this was before we learned about DP, so we were supposed to use like the suboptimal solution of doing stuff technically, which will come up later. So this means that like this thing, this mac or this opt j minus one is basically saying, oh, skip this job, skip this job, skip this job. And then this is like the zero case, skip this job. And then there's also this opt p of j. Now, because of the fact that all of these jobs overlap, p of j is like saying, oh, what's the earliest or latest previous job I can take, or the next previous job I can take if I take this job. If you take this job, all the other jobs are eliminated, which means that like this case here goes directly to the zero case. This one goes directly to the zero case, directly to the zero case. So you can see, assuming you can read my handwriting here, my calligraphy, that there are two n arrows because each of the overlapping intervals is basically saying, okay, I can either skip or I can take myself, which will directly go all the way back to 0. So there are always two end calls. Then this one, if none of the jobs overlap, then two end calls are made. We can like represent it like this, perhaps. This means that these two statements are like equal. So at first glance, when I was taking the test, I was kind of mad about this because if you're doing this the DP way, you could either do like the minus ones, right? This case, left case here, or you could do the take the optimal of the previous case, which would theoretically just be like this. And I was like, oh wow, it's just 2n as well. He was saying this was like before we learned DP. So what it would end up being is like here for this one, you can like go back one, or you could choose the optimal of this one, which is to go back one, or to choose the optimal of this one, which is to go back one, or to choose the optimal of this one. But then you like have to compute this one as well. And so basically it's this annoying, like it's the recursive calls that just end up calling each other. So this one's like this or this, and then this one is this, or this, which becomes this, and then this one is this, or this, because basically the ops aren't memoized, so you have to recompute them every single time, and it just becomes super duper messy. With the overlaps, or when they're all overlapping, that didn't become a problem because these were all like going straight to 0. Both of these opt calls were going straight to 0, so you never had to like call another one of these. I think in this exam, if there's something like this, he would specifically saying this is without memoization because now we've learned DP. So that's why this one is wrong. This one was like not true because we went over here, clearly that was going over like all of them or whatever. Actually, I can go more. Sorry, I'm like tired. If none of the jobs overlap, the fastest way to solve the problem is O of n. This is pretty obvious. If none of the jobs overlap, you just take them all. So you iterate them and go like, oh, +1, +2, +3, +4. You add all their weights up. So yeah, that's why that one's correct as well. Yeah, this quiz was weird. I heard someone say that they had like a 10 at the start, and then by the end they had a full 25 because they all got yeah, and yeah, I honestly after I took this exam, I typed up like a Canvas message to this guy. It's like, oh, that exam was whack. Because I was like, yeah, this question is just like he was just gaslighting us and himself apparently because of no, not this question because he said it was O of 1 first, and then yeah, and then this too I saw was wrong on the exam. Points. I like how it says it's wrong. What's this? That was me. I did too. Well, good job, you guys. 25 points, just like that. Yeah. So that's that. Oh, I guess I did miss this one answer choice. If every pair of jobs overlaps, there's an O one time algorithm. You still have to like go over them and like maximize all the intervals. So there's no O one. Definitely not. But honestly, like I was convinced when I was taking these tests, like these two are right. And I was like, I was pulling back my SAT test bank, testing like strategy. I'm like, these two are the similar, which means like one of them has to be right and one of them has to be wrong. So I just chose this one. But hopefully the exam will not have the same issues as this. You think so? Okay. Mhm. Yeah, yeah. Well, I guess if you can understand these, I mean, there's a lot more new content since this. We do have network flow and DP, but which, is what our get out of here, which is what our things are on, knapsack and network flow. But I don't know how this algorithm works, know why this works, know how to trace it back. And hopefully you'll do okay.
Thank you for your time, Max. Mwah.
I just want to say real quick for anyone online that's like talking, I can't hear you because there's no like sound in this room. I guess I could turn it on. whatever, just message in chat. Um, exchange argument. Mhm. Mhm. Yeah, right. Yeah, I don't, yeah, I would think it's more like induction thing. Because okay, exchange argument, I remember coming up on like the last exam with like the like greedy interval scheduling where it was like, okay, assume the greedy way is like not correct. And then like you would show why like that other way of doing it would just you could just like exchange that greedy way of doing it. Yes. Um there it would make sense, but do you happen to know like what slides? Mhm. Here are his slides, by the way. DP said, yeah, like this. Um, I, I think it's also that's kind of like not select job I, select job J. Okay, optimal substructure. Did he say something here about like optimal substructure property? Because maybe I would think like, yeah, maybe I would think the idea is like, yeah, it does just say it, doesn't it? Just throw it in there. Yeah. Um, maybe, okay, what I would assume is maybe this is like, there's two cases, right? It's saying like, if you take the less, or if you take the more optimal case, that can always be like exchanged into the less optimal case. Greedy algorithms. I'll get to the questions in the chat quickly. Yeah. Yeah. I don't know. I guess if you know what's going on with the greedy ones, I think you'd probably be able to like figure it out on the exam, hopefully. Yeah. Mhm. Right, right. Yeah, yeah. So like for the sub cases, you can always kind of exchange the more optimal one into less. Okay, what does people in the class say, chat saying? Could I post, yeah, I'll post the link to the recording. Oh, I have to like stay here in this classroom and wait for the 2-hour recording to finish. Whatever. All right, anything else? Actually, I'll stop the meeting now. So it starts converting. See you guys on Zoom.